In this video, I'm going to go through 4.4 intermolecular forces. There are three learning outcomes that I'm going to cover in this video. The first one is describe intermolecular forces, which include van der Waals forces, hydrogen bond. Second learning outcome, I'm going to explain factors that influence van der Waals and hydrogen bonds. And the third learning outcome, I'm going to relate the effects of hydrogen bonding on boiling point, solubility, and density of water compared to ice. First, what is intermolecular forces? For the attractive forces acting between atoms in a molecule, we call it as intramolecular forces. For attractive forces acting between molecules, we call them as intermolecular forces. Intermolecular forces require molecules to be in close proximity in order to take place. And intermolecular forces are important because it will govern the physical properties of a substance, such as the melting point, boiling point, density, and etc. There are two types of intermolecular forces that I'm going to cover. The first one is van der Waals forces, which include London dispersion forces and dipole-dipole forces, and the second one, hydrogen bonds. And the strength of intermolecular forces increase in the order of London dispersion forces being the weakest, followed by dipole-dipole forces and hydrogen bonds being the strongest. There are two types of van der Waals forces. The first one is London dispersion forces, which is the attractive forces between instantaneous dipole and induced dipole. London dispersion forces present between all atoms and molecules. So how do London dispersion forces form between atoms or molecules? On average, the electron or negatively charged of an atom is evenly distributed around the nucleus as in the diagram. At one instant, when the atom or molecule move, one side of the molecule or atom will have higher electron density and become partially negatively charged, while on another side, it will have lower electron density and become partially positive charge. At this instant, the atoms or molecules has a small instantaneous dipole, and this instantaneous dipole is temporarily dipole. And this instantaneous dipole then will induce the neighboring atom or molecule to cause the neighboring atom or molecule have induced dipole. Means that one side will become partially positive charge and another side will become partially negative charge as well. And this induced dipole on neighboring atom or molecule, we call it as induced dipole. And what is London dispersion forces? It is basically the attractive forces between the instantaneous dipole and induced dipole. So this is the London dispersion forces which form between atom or molecule. And these London dispersion forces can only form when the atoms or molecules they are in close proximity. The second type of van der Waals forces is dipole-dipole forces. So dipole-dipole forces is the attractive forces between partially negative end of permanent dipole of a molecule with partially positive end of permanent dipole of another molecule. So for dipole-dipole forces, it present between polar molecules. So for polar molecules, between them, they are London dispersion forces and dipole-dipole forces. And the dipole-dipole forces will be dominating because dipole-dipole forces is stronger than the London dispersion forces. So how dipole-dipole forces could be formed between polar molecules? So for polar molecule, due to one atom being more electronegative than another atom, therefore the end with more electronegative atom will permanently be partially negatively charged, and the end with less electronegativity will permanently be partially positive charged. And therefore, in a polar molecule, there is a permanent dipole. And when a polar molecule is in close proximity with another polar molecule, then the partially positive end of the molecule will be attracted to the partially negative end of another molecule. And these attractive forces between them is called dipole-dipole forces. Again, for dipole-dipole forces to be significant, the polar molecules need to be in close proximity, and dipole-dipole forces will become stronger when the molecule become more polar. Now we move on to look at the factors affecting the strength of van der Waals forces. The first factor is molecular size. Larger the molecular size, stronger the van der Waals forces between the molecules. So how do we determine the molecular size? By looking at the molar mass. Again, larger is the molecular size, means that greater is the polarizability of the molecule or atom. Therefore, the van der Waals forces between the molecules will be stronger. For example, between Br2 molecule and F2 molecule. So Br2 molecule having larger molar mass. Therefore, Br2 molecule has larger molecular size than F2 molecule. And Br2 molecule therefore has greater polarizability and therefore stronger van der Waals forces between the molecule compared to F2 molecules. When the van der Waals forces between molecules are stronger, that means that more heat energy is needed to overcome the van der Waals forces between the molecule, and therefore Br2, which has stronger van der Waals forces between molecule, has higher boiling point than F2 molecule. The second factor affecting the strength of van der Waals forces is molecular shape. We only look at the molecular shape as the factor when comparing the molecule with same molar mass. For example, pentane and 2,2-dimethylpropane, both having same molar mass, and we then can compare their strength of van der Waals forces based on molecular shape factor. For molecular shape, the linear shape molecule, no branch, will have larger surface area in contact between molecules, therefore having stronger van der Waals forces compared to those molecules with branching. For example, pentane is linear in shape, having no branching, so linear in shape, but 2,2-dimethylpropane having branching. So pentane being in linear in shape because no branching will have larger surface area in contact between molecules for van der Waals forces. Therefore, we will expect the van der Waals forces between pentane molecule to be stronger compared to 2,2-dimethylpropane. And therefore, pentane will have higher boiling point than 2,2-dimethylpropane. The third factor affecting the strength of van der Waals forces is polarity of a molecule. When the molecule becomes more polar, the strength of van der Waals forces between molecules increases. Therefore, polar molecules have greater strength of van der Waals forces. For example, ethane. Ethane is a non-polar molecule. So, between ethane molecules only have London dispersion forces. While fluoromethane is a polar molecule. So between fluoromethane, there are London dispersion forces and also dipole-dipole forces. Therefore, we will expect the van der Waals forces between polar molecules to be stronger, and we are expecting fluoromethane to have higher boiling point, because between fluoromethane, there are dipole-dipole forces present, and these dipole-dipole forces are stronger than the London dispersion forces. So more heat needed to overcome stronger van der Waals forces between fluoromethane molecule, and therefore fluoromethane has higher boiling point than ethane. Now we move on to look at the second type of intermolecular forces, hydrogen bonds. What is hydrogen bond? It is the attractive forces between the partially positively charged hydrogen atom bonded to either fluorine, oxygen, or nitrogen of a polar molecule with the partially negatively charged electronegative atom of another molecule. And this partially negative charged electronegative atom of another molecule can either be, again, fluorine, oxygen, or nitrogen. For example, in ammonia, between ammonia molecule, hydrogen bonds could be formed because in one ammonia molecule, the hydrogen is partially positively charged because it is bonded to nitrogen. On another ammonia molecule, the nitrogen is partially negatively charged because nitrogen is more electronegative than the hydrogen. And what is hydrogen bond? Hydrogen bond is the attractive forces between the partially positively charged hydrogen atom of a polar molecule with the partially negatively charged electronegative nitrogen of another molecule. So this is the hydrogen bond between ammonia molecules. In acetic acid, where is the hydrogen bond? It is between the hydrogen, which is partially positively charged because it is bonded to oxygen atom, with the partially negatively charged electronegative atom oxygen of another molecule. So this oxygen is partially negatively charged. And the attractive forces between the partially positive charged end of hydrogen with the partially negatively charged end oxygen of another atom. So this is the hydrogen bond between the acetic acid molecules. And in methanol, why is this the hydrogen bond? It is because for this molecule, the hydrogen is partially positive charged because bonded to oxygen. And on another molecule, the oxygen is partially negatively charged because being electronegative, more electronegative than carbon and hydrogen. And the attractive forces between the partially positive charged hydrogen atom with the partially negatively charged oxygen of another molecule is the hydrogen bond. And this hydrogen bond is much weaker than the intramolecular forces, such as ionic bond and covalent bond, but much stronger than the Van der Waals forces, such as dipole-dipole forces or London dispersion forces. There are two factors affecting the strength of hydrogen bonds. The first one is electronegativity. Nitrogen is less electronegative compared to oxygen and fluorine, and oxygen is less electronegative compared to fluorine. By knowing this, then we will expect water to have higher boiling point than ammonia, because hydrogen bonds between water molecule is stronger than between ammonia molecule, since oxygen is more electronegative than nitrogen. And the second factor affecting the strength of hydrogen bonds between molecules is number of hydrogen bonds that could be formed between the molecules. Fluorine is more electronegative than oxygen. So we will expect hydrogen fluoride to have higher boiling point than water. But in real life, hydrogen fluoride has lower boiling point than water. Why? It is because between water molecule, more hydrogen bonds could be, while for hydrogen fluoride, less number of hydrogen bonds could be formed between the molecule, causes hydrogen fluoride to have lower boiling point than water. Last learning outcome, the effect of hydrogen bonds on physical properties of a substance. The first physical properties that we are going to look at is boiling points. So we are going to look at the boiling points of hydride of element group 14 to 17. We shall look at the group 14 elements first. For group 14 elements, basically the boiling points displays normal behavior because there is no hydrogen bonding involved between the molecules. As no hydrogen bonding involved between molecules, so means that only Van der Waals forces present between the molecule. And from CH4, SiH4, GeH4, SnH4, we know that the molecular size increases due to increase in the molar mass. As the molecular size increases, we will expect the Van der Waals forces between molecules to become stronger from CH4 until SH4. Therefore, the boiling point is expected to increase from CH4, SiH4, GeH4 to SnH4. However, if we look at group 15, group 16, and group 17, we see the abnormal behavior between ammonia, HF, and water. Even though their molecular size are smaller than the rest of the hydride, but their boiling point is still much higher compared to the other hydride of their group. Why? If we exclude water, HF, and ammonia, we can see that the hydride of group 15, 16, 17 still having normal behavior. Why? It is because for this group of hydride, there is no hydrogen bonds present between the molecules only when there are forces involved. And from HCl, HBr to Hi, the molecular size increases, causes the van der Waals forces between the molecules to become stronger, and therefore the boiling point increases from HCl, HBr to Hi. For group 16 hydride, the molecular size increased from H2S, H2Se, H2Te. Therefore, the van der Waals forces is expected to increase from H2S, H2Se to H2Te. Therefore, the boiling point is expected to increase from H2S, H2Se to H2Te. For group 15 hydride, the molecular size increased from pH3, ASH3 to SpH3. Therefore, we will expect the van der Waals forces to increase from pH3, ASH3 to SpH3, and therefore the boiling point increase from pH3 to ASH3 to SpH3. For water, HF, and ammonia, that shows abnormal behavior due to the presence of hydrogen bonds between the molecule, and the hydrogen bonds are stronger than the van der Waals forces, causes water, HF, and ammonia to have higher boiling point than other hydrides of their group. And water having highest boiling point, followed by HF, followed by ammonia. Even though fluorine is more electronegative than oxygen, water is still having higher boiling point than HF because between water molecule, more hydrogen bonds can be formed compared to between hydrogen fluoride molecule. And for HF, it has higher boiling point than ammonia because stronger hydrogen bond can be formed between hydrogen fluoride molecule due to fluorine being more electronegative than nitrogen. The second effect of hydrogen bonds on the physical properties of a substance is solubility in water. To be able to dissolve or soluble in water, basically the substance must be able to form hydrogen bonds with water. For example, ammonia. Ammonia can form hydrogen bond with water molecule. Therefore, ammonia is expected to be able to dissolve in water. For the substance that are insoluble in water, basically they cannot form hydrogen bond with water. Like for example, chloroform and also hydrocarbons such as C2H4 and C6H6, they are nonpolar and cannot form hydrogen bond with water, therefore they are insoluble in water. Hydrogen bonds also affect the density of water and ice. For most substances, the solid are denser than liquid because solid more closely packed than liquid. But ice is less dense than the water. Why? It is because when water is being cooled to become ice, the water molecules in the ice will arrange themselves in a tetrahedral arrangement in such a way to maximize the number of hydrogen bonds that can be formed between the water molecule. And these result in open structure formed in the ice. And this open structure causes ice to have large empty space and therefore lower density than the liquid water. In this diagram, we can see that when forming ice, the water molecule will arrange themselves tetrahedrally in order to form maximum 4 hydrogen bonds with other water molecule. And this result in open structure being formed in the ice. And we know that density is equal to mass over volume. In ice, due to the water molecules arranged in such a way to maximize the hydrogen bond formations between water molecule and result in forming the open structure, causes ice to have large volume and therefore lower density than the liquid water. When ice melt become water, some of the hydrogen bonds are broken. In liquid water, water molecules do not need to form maximum 4 hydrogen bond. As they do not need to form maximum 4 hydrogen bond, means that now the water molecule can arrange themselves more closely to one another. Therefore, density is equal to mass over volume. In liquid water, as water molecule can pack more closely to themselves, therefore liquid water will have smaller volume and therefore larger density. And because of this, we can see the phenomena such as ice floats on the surface of water.